Sometimes during the year, the sun is up all of the time. Other times during the year, the sun is down all of the time. And when we landed on May 25th, we landed in the early part, or the early part of the summer, late spring, to try to maximize the amount of time that we would have the sun above the horizon. However, on Sol 93, as it turned out, that was the first Sol that we actually had the sun dip completely below the horizon. And as a matter of fact, we have a video. Can we show this video? This was a video that was shot, a series of images that were taken on Sol 101, which is showing the sun rise above the Arctic horizon. Actually seeing sunrise here. We could play it in reverse and see the opposite. But this is actually what we're facing now. And as it turns out, we can stop the video now. Okay. As it turns out, even though the vehicle was designed strictly to operate during the 90 sols, we know that we have enough energy in the vehicle to survive and continue operating further. And that's why, Doug, as Doug explained, we've extended the mission beyond that. As the Martian winter approaches, and I'd like to show a curve, please. Can you bring up the last slide? As the Martian winter approaches, we lose sunlight. The curve you're seeing here, if you see a green slash, that's where we are today, which is approximately Sol 123. Of the 24 hours and 40 minutes that is the duration of a Martian sol, the sun is below the horizon right now, a little over 4 hours of that sol. But you can see as that curve steepens out, it's actually going to go below the horizon longer and longer. And eventually, when it gets in, you can see the date annotated there on April 1st, the sun is actually below the horizon for a good 3 months. So by the time we get to April, there'll be no sun up there, and that hurts the vehicle in quite a few ways, which I'll explain in a little bit. However, after the sun starts rising, which is about 3 months later, sometime in the early July time frame, we start getting more and more energy, and the vehicle will probably not survive that. But there won't be enough power on the vehicle, if anyone is thinking, for it to reasonably come back to life until the October time frame, although nobody anticipates that the vehicle survive that harsh winter. However, one of the consequences of the fact that the sun is going down is we actually have two problems. Number one, we are producing less energy. Obviously, as the sun is low on the horizon and dipping below the horizon, we produce less energy per sol. And the second thing that's working against us as well is we're consuming more energy. As the temperatures get colder and colder, the vehicle has to produce more energy to its heaters to keep the electronics from freezing. So both these things conspire against us and take energy away from the science that we would like to do with the vehicle. So we're trying to literally make hay as the sun shine and really try to get the most out of the science instruments in these last few days before the end of the mission. To put some numbers on that, when we landed in late May, and probably for about the first month of the mission, we were actually generating about 3,500 watt-hours every sol, which was plenty of energy to do lots of our in situ or on-surface instrument experiments. However, last Friday on Sol 120, the information we got was the vehicle produced 2,100 watt-hours in that given sol, and it's slowly going down and down to the point where we're going to become a weather station with occasional images. But up until that point, we're going to try to squeeze every bit of science out of this mission from now until whenever it is the terminal date. And with that, I'll throw it over to Bill to talk a little bit about the TIGA.
Thank you, Barry. Well, I'd like to talk about some of the really exciting results we're finding with the TIGA instrument. We've identified several minerals that are indicators for interaction with water in the past. Now, some of these minerals have been found by remote sensing via orbiters, but only in areas on the planet where there's been evidence for flowing water in the past. What's new here is that we've seen evidence for in the northern plains, kind of in the wide open spaces where there really is no evidence for flowing water. So that's one of the things we're really excited about. But before I go on to talk about those results, I should tell you about TIGA and how it works. It's a somewhat complicated instrument. TIGA stands for a Thermal and Evolved Gas Analyzer. It has 8 small ovens which heat up the soil samples, and it has an evolved gas analyzer which sniffs the gases that are given off as the sample is heated. Now, knowing the nature of the gases given off is actually very useful in identifying what's in the oven. It's very much as if you walk into a kitchen where chocolate chip cookies are baking, and you can immediately tell from your nose what's in the oven. Okay, let me give you a picture now. If you can show this first video of how it works. The robotic arm scoops up some soil and it delivers it to Tiga. Here it's going to pour it into one of the cells containing one of the ovens, and it falls into a funnel, goes past a little rotator thing called a whirligig that disturbs the soil and makes sure it doesn't get stuck in the funnel. And it falls into an oven. We then seal the oven, heat it up, gets red hot, as you can see, and the hot gases are then passed along to the evolved gas analyzer, which tell us what's happening. Okay, next what I'd like to do is talk about the locations where we got our samples. If I can have the first still picture, please. Here you can see a picture of the ground looking down from the imager. Off on the right is just the edge of the solar panels, and you can see 3 little white squares are actually of sunlight passing through holes in the solar panel. The area of interest is the darker part of the scene, right in the middle. You can see where there's a trench where we've actually scooped up our samples. Tiga's analyzed samples from the surface and at several levels of depth. Well, the first material indicative of formation with liquid water that I'd like to talk about was found by Tiga on the basis of a high-temperature release of water vapor. It is most likely due to a clay mineral, which is in the class of minerals called sheet silicates. The best-known example of a sheet silicate is mica, but in this case we're not looking at mica. We're looking at a different type in which a form of water actually is in the crystal structure between the different sheets. And it's this water which is between the sheets that makes the clay minerals much softer than mica, for example. In this case, our identification is somewhat ambiguous. There are a few other minerals which could release water vapor at high temperatures, but we think the sheet silicates or the clays are probably the most likely. The other important mineral we found is a carbonate. And this also points to the presence of liquid water. It's actually calcium carbonate. And this mineral was identified by Tiga on the basis of a high-temperature release of carbon dioxide gas. Now, in this case, our identification is unambiguous. The release of carbon dioxide gas can only come from a carbonate, and the fact that it was released at high temperature means it's really the calcium carbonate as opposed to some other forms such as iron or magnesium carbonate. Now, carbonates are very common minerals on Earth. They commonly form by the interaction of liquid water with carbon dioxide gas, and that's just what we think is going on the surface of Mars. Another form in which people are familiar is just common chalk that you use for writing on blackboards. And another use of it is in the form of antacids, where if you have acidic stomachs, you can take one of these things and it will lower the acidity. Well, in fact, our next presenter, Mike Hecht, is going to be talking about the aspect of calcium carbonate and its ability to neutralize acids, which was actually the basis for identification of this mineral based on another Phoenix instrument, the MECA instrument. Mike?
Thank you, Bill. MECA is a suite of instruments that includes 4 wet chemistry cells, it includes 2 microscopes, and it includes a conductivity probe at the end of the robotic arm. We've been enjoying a feast of data from these instruments for the last 4 months. I'll tell you a little bit about all 3, including additional evidence for the 2 materials that Bill Boynton just told you about. So let's start with the chemistry. Now, one of the first findings we announced